Hello, and welcome to this week's Ethical Dilemma in Science. We're going to take a look at air conditioning and global warming and ask the question, is this a cool, refreshing breeze and or possibly a frigid finger of impending doom? So I pre-recorded a introduction to this.
So, for the ethical dilemma in science this week, we're going to take a look at some issues associated with air conditioning. But first, in order to understand air conditioning, I was thinking about an example this morning on my morning run. So, I've just finished a 4-mile run. It's the last week of July, just north of Philadelphia. We're in the midst, actually in between two heat waves. So, we had a pretty extended heat wave that ended a couple days ago, which was really awful. And they're saying that another heat wave is going to be coming in. But basically, looking at me, I'm a disgusting mess, 4 miles, and I'm coated in sweat. And so when we take a look at sweat, we're looking at a process that is normally occurring within our body to cool the body during hot times. And right now, it's about 70 degrees out, about 96% humidity. Which means I'm sweating a lot and not necessarily getting a whole lot of cooling effect from that. And so we're going to take a look at how the body cools itself, and then take a look at how air conditioning cools our living spaces and our workspaces.
Okay, so the basis for this week's Ethical Dilemma in Science is a couple articles that have come out relatively recently. And so July 2022, a couple articles, when weather gets hot enough to kill, different examples of heat waves around the globe. I just pulled one example here. Heat wave kills more than 2,000 people in Spain and Portugal from earlier this month. Lots of different examples of this from all over the world, as well as we can see within the United States. So again, another article, July 2022, taking a look at the summer temperatures. And so in this graphic, what we're seeing is basically going from kind of light blue all the way up to kind of through yellow, through orange, through red, into higher temperatures. And what they're doing is comparing the temperature from about 1971 to about 2000, compared with the last 4 years, so 2017 to 2021. And so what we can see is that even though, kind of a central region in kind of the middle of the country, kind of towards the south, hasn't really changed a whole lot. We're seeing kind of the yellowish and orange through kind of the upper Midwest, the kind of upper kind of northeast portion of the United States. And then we're pushing into the heavy oranges and reds as we look into the American Southwest. So looking at this, looking at this as an example of it's definitely getting hotter. We can debate as to what the causes of that increase in temperature are, but it is becoming hotter kind of around the globe, and it's impacting on both human life as well as animal life as well. And so to start looking at this, again, the effect of heat on the human body, kind of starting out with about 120 years ago, John Scott Haldane was a Scottish physician and physiologist that basically was interested in studying kind of the conditions, the kind of extreme conditions, extreme environments that the body can be exposed to, and how it responds to it, how the body responds to it. So prior to Haldane's work, there had been another scientist that had gone down deep within a mine and basically found out that the human body could tolerate temperatures up to about 115 degrees Celsius. And so 115 degrees Celsius, 100 degrees Celsius is boiling. Boiling temperatures, boiling water. Put it into Fahrenheit for those of us that are metrically challenged, that's about 240 degrees Fahrenheit. But the body can sustain that if it's dry heat. And so we'll talk about why that is in a minute. But basically, kind of the dry heat kind of allows the body to kind of cool itself through the process of sweating. In contrast, Haldane went down into a mine which was very moist, and basically his work showed that after about 3 hours at 31 degrees Celsius, so much lower than that, the body started to have problems. Increase in pulse, increase in body temperature, starting to start to impact kind of the cognitive abilities. And so because of that, and further research, basically came up with this kind of upper limit to or I guess lower limit to the temperature that the body is able to sustain. So it can be higher if you've got dry heat, but in the area of moisture, humid heat, the body is very, very limited in its ability to respond to these higher temperatures. So a number of studies, this is one from 2021 that I'll link to in the notes below, have taken a look at the temperature thresholds for life. And for many organisms, their preferable temperature is in a temperature range that is much, much lower than the temperatures we're seeing now appearing throughout the summers. So as promised, and as a follow-up to that awful video I recorded a couple of days ago after my run, the human body kind of responds to an increase in temperature by sweating. And so basically what happens is you're going to have a series of sweat glands along your body. They are going to secrete a watery secretion, but release a watery secretion, maybe some ions on it. This is going to coat the surface of the body with sweat. And then as that sweat evaporates, the process of evaporating, you basically, without going into a lot of the chemistry and the physics involved, basically the water molecules in your sweat have to have enough energy to evaporate, have enough energy to kind of break free from the liquid surface along along your skin and go into the atmosphere to evaporate. And so in the process of that, they're going to take the energy in the form of heat energy and draw that away from the body. And so in doing so, they pull the heat energy off into the air, and it has a cooling effect. And now as that hot air is rising with that hot water vapor, cool air is going to come down kind of close to the skin, and that whole process is going to be repeating itself. So in the video I had, where I was at 96% humidity, sweat was pouring off of me. It wasn't really evaporating, so I wasn't getting much of an effect for cooling for the amount of sweating that I was doing at that time. And so what we can see, and again, a follow-up of Haldane's work and examples that we can all see if we're out in the summer, is that humidity has a very dramatic effect on the way our body responds, how we feel about that temperature. And so the way that that's measured, if you listen to the weather reports on the news, they'll often talk about the relative humidity, they'll talk about the dew point, and so that dew point is a measure about how much humidity in the air. And so basically the way they calculate that or determine what it is that they've got two thermometers. The first thermometer is going to be a dry bulb thermometer, and that's like a normal thermometer. It's basically going to tell you what is the air temperature outside. But then they're going to have a wet bulb thermometer. In this wet bulb thermometer, they basically got a little bit of gauze over it, a little bit of distilled water, and so you've got water covering the tip or the bulb of this thermostat, and as that water evaporates, it's going to do the same thing as sweat evaporating from your skin. That water evaporating is going to cool this thermometer, and so you'll see a difference occurring between the dry bulb temperature and the wet bulb temperature. And the closer those two things are to one another is going to be an indication of kind of higher levels of humidity. And so if we drop that into kind of a fancy chart, and the numbers are small, so we don't have to necessarily worry about them, what we can see is that the numbers here kind of in blue, and everything over here to the left and down from this blue is going to be blue. And so that's going to be relatively dry air. The green air is going to be comfortable. The yellow air, sorry about that, is going to be, all right. But when you start pushing into these oranges and reds, you're going to be getting into higher levels of humidity that are going to make it really, really uncomfortable. And so if we can see that at these higher levels of humidity, even at a lower temperature, we got temperature along the y-axis, humidity along the x-axis, at these high levels of humidity, even a cooler temperature outside is going to be kind of getting into that uncomfortable stage. So much so that if you listen to the weather report, they're going to be telling you, kind of the danger zone And everybody says it's not the heat, it's the humidity. It's an awful statement, but it's actually true. What you can see, and I guess again looking at kind of a small portion of that dew point chart, putting it into kind of a different indication. You got air temperature along the y-axis here, relative humidity along the x-axis. What you can see again, like I said before, the higher the humidity is. Here's 100% humidity, where it's basically water is sitting in the air, and you're not going to be able to evaporate sweat off your surface. You can see that a much lower temperature is going to be getting into those extreme danger ranges. And that's where you're going to get those heat warnings, where they're going to tell you, don't go out, don't exert yourself, make sure you're drinking a lot of water, check in on friends and relatives that may not be able to kind of take care of themselves or may have limited access to cooling. And so when we get to that, how is it that we're going to cool the body? But before we go there, I wanted to touch in one final study. This is a study that just came out the end of last year in the Journal of Applied Physiology, where they're basically looking at this using empirical evidence. Not how awful does it feel when you're out in the heat and when it's humid. But when you go through and actually do physiological measurements, you start looking at things like the ability to sweat, the heart rate, the ability to basically compensate for those differences in temperatures. And so what they're able to show is that even without getting to that theoretical adaptability range, that range of 35 degrees of moist heat, you start to see the body kind of down through here starting to have difficulty responding to the temperature, basically kind of adapting to that temperature or basically tolerating that temperature. And at that point, it becomes uncompensable. Whatever that word is. Basically, the body can't respond to that level of heat by getting the heat and emitting it from the body. And so that heat will start to accumulate in the body, and that can cause both heat exhaustion and heat stroke, which I'll touch on at the very end of today. But basically, in these high moist temperatures, these high humid temperatures, it becomes very, very difficult for the normal physiological functions within your body, and it can contribute to feelings of illness, feeling of sickness, and in very severe situations, it can contribute to death, as we saw in those news accounts kind of at the start of today's ethical dilemma. So if we take a look at this, one of the ways in which human beings respond to increased temperatures is to sit in air conditioning. It's what I did. I came in, took a shower, and then sat down in my office, which has air conditioning, and felt a whole lot better. In a 2018 report by the International Energy Association, they were reporting that 5 years ago, 6 years ago, in 2016, about 10% of the global energy consumption was based on cooling, based on running air conditioners and electric fans. But as a follow-up to that, they said that less than 10% of the 2.8 billion with a B, people in the hottest parts of the world, those that have an average daily temperature above 25 degrees Celsius, owned an air conditioner. And so, only about 8%, less than 1 out of 10 people in the hottest parts of the world have the air conditioner, which would give them relief from that heating. And then a follow-up study by The Economist, taking a look at it here, in the United States, going from 2010 to 2050, we can see that even in the lowest income level here, we're still above 75-80% with access to air conditioning, and that's expected to go up a little bit over the next 40 years. In contrast, other regions, equatorial regions of Africa, South Africa, regions like Italy within the Mediterranean, South America, Asia, where we've seen kind of low levels of access to air conditioning, are expected to increase pretty dramatically over the next 40 years because, as this title says, let's see if I can get out of the way, in a hotter world, air conditioning isn't a luxury, it's a lifesaver. It's the ability to get out of that hot, humid air in an effort to kind of prevent kind of overheating of the body. And because of that, the increased need for air conditioning, the energy consumption is expected to triple by 2050. And so dramatically increase the amount of energy that's used for cooling people off. Excuse me. And so that gives rise to how does an air conditioner work, and how is this similar to what we're seeing in the human body, and the human body kind of cooling itself through the process of evaporating sweat off of the surface. And so there are 4 basic steps that are going to be found in an air conditioner, and they've been relatively stable since it was first invented over, I guess, 110 years ago now. So you're going to have refrigerant, basically a material that can go from a liquid to gaseous state that you pump through the series of pipes. At the first stage here, we've got a compressor that's going to pull that refrigerant in. That refrigerant comes in, increases the pressure of that refrigerant, and that's going to cause that refrigerant to heat up. And so at that point, we're compressing it, we're heating it up. That hot refrigerant then is going to go through this condenser over here at number 2. And that condenser is basically going to be a series, almost like a radiator in your car. We're going to blow room air or house air over that. It's going to blow through, and that's going to take that. It's going to heat the air and then blow that air outside as it's going through. But you're going to take that hot refrigerant, and the air blowing over it is going to cool the refrigerant down. So this cooler refrigerant then is going to get over here. Make sure I get over here, number 3 with the expansion valve. And that's going to allow the refrigerant to kind of expand. It's going to increase in volume. And that increase in volume is going to decrease pressure, allowing that refrigerant then to go from warm to really, really cool. And so, if you study physics and chemistry, there's some gas laws that go along with it. But basically, as that refrigerant becomes less dense, as that volume increases, it's going to cool off. And then because of that, we're going to run it through another series, almost like another radiator over here, in which case we're going to have this cold refrigerant going through. We're going to blow air through that, and that air as it blowing through is going to go from whatever temperature is, pick up some of the coldness, basically transfer its heat into that refrigerant, so that the air being kind of blown out of a refrigerator, out of a air conditioner is going to be refrigerated. It's going to be cooled, and so we're going to be blowing cool air to the inside of a room or inside of a house. Now, in doing so, that cooler air is going to be less able to hold water vapor within it, and so that water is going to drop out, and so the process of cooling the air is also going to dehumidify that air. And then we're basically going to get over here to the end. We're going to go here with that cool refrigerant that has picked up some of the warmth from the air as it cooled the air from the air conditioning. And that cool refrigerant then is going to go through the compressor, be compressed down, and then that's going to become the hot refrigerant again, and that whole cycle continues over and over again. Very energy intensive because you've got all of these fans, you're running compressors to kind of condense the gas down, compress it in to get this change between the high pressure and basically high pressure, low volume, and low pressure, higher volume system over here. The whole ability to go back and forth with this allows us to pull the temperature, pull the heat energy out of the air. And so it's a great process. It works really, really well. The problem is, if we take a look at that previous slide, if you've got lots of these air conditioners kind of sitting in kind of a busy urban environment, they're going to be pumping hot air to the outside. So where it's already hot, we're going to be continuing to pump out heat into that surrounding environment. And so that gives rise to the question then, how do we prevent air conditioners from heating the planet? It sounds like a bad B movie. We're going to get, Attack of the Air Conditioners. But if we take a look at this, a number of studies over the last 10 years have taken a look at what's referred to as anthropogenic heating. This is man-made heating of the environment. And so in studies from Germany, from Singapore, in the United States, within Phoenix, Arizona, they've looked at the impact of human activity on the environment in the region. And what they've been able to show is that buildings have the highest contribution to urban heat. So basically, you got big concrete buildings. They're going to absorb heat during the day and release that heat at night and contribute to basically urban heat islands, which we'll talk about next week in the ethical dilemma and science. Some estimates as much as 3.7 degrees Celsius. So raising that city environment, the buildings have the potential to raise it about 5 degrees Fahrenheit. So pretty big contribution. The next highest contributor was going to be air conditioning systems. And so air conditioning systems can contribute about 1.4 degrees Celsius. So they can contribute to the warming of the environment outside of them. And so because of this, we're running into this situation then where we've got limited amount of electricity that's available. Air conditioning is taking and cooling is taking a large amount of energy from a variety of sources. And there's this idea and this fear, because we're seeing it happen, that as people use more and more of these air conditioners, they're going to be contributing to potential stresses on our electrical grids that are delivering electricity to us. And we've got a limited amount of electricity that becomes available. So some places are encouraging people to, don't turn your air conditioners down as low. This is a report from Japan, setting your air conditioner at 82 degrees. And I guess turning off the heated toilet seats, that's a whole separate issue. But basically this idea that if we are overcooling, we are going to be putting stress on the system, and that stress on the system could result in a breakdown and a power outage, which would really disrupt the ability of everybody to get air conditioning. In addition, there have been studies that look at the human body and the body's ability to respond to heat. And what they look at basically is an idea of heat acclimatization or climatization. Basically, how the body kind of learns to or adapts to the ability to withstand higher temperatures. So in my example, I went out, I ran 4 miles. It was cool, it was in the 70s, but high humidity felt really, really oppressive. I can tell you, if I had started doing that back in May, it really would have been difficult. It would have been painful. But I've been doing that, on a fairly regular basis for the entire summer. So my body is able to respond to that. But people have shown that if you're not going through this acclimatization process, your body then isn't able to respond as well to these higher temperatures. So as promised, we're getting down to the end here. Just starting out, because we are talking about global warming, we're talking about heat, we're talking about air conditioning. Please make sure, I'm not sure what happened there, please make sure that you're aware of the symptoms of both heat exhaustion and heat stroke. Both of these are severe. Heat stroke is much, much more severe. But exerting yourself, or in some cases even in high temperatures with high humidity, even without exertion, you can get into a period of heat exhaustion. This is where the body is starting to have a hard time responding to this increase in temperature. So you're seeing an increase in thirst, heavy sweating, start to feel nauseous, potentially a little bit of weakness and dizziness going on. And these are warning signs. And if this is occurring, get out of the heat, get out, get into a cooler area, get into the shade, drink some cool water. And if this persists, seek medical attention. I'm not, a doctor giving medical advice here. I'm a different type of doctor from that. But recognize the very, very severe signs of heat stroke. This is in many cases when that heavy sweating stops because the body just can't respond to the amount of heat that becomes. Individuals that are going into heat stroke, and again, heat exhaustion, if it's not treated, can go into heat stroke, will start to become confused, dizzy, in many cases not sweating, and they become could become unconscious, and at that point, they're going to require emergency medical attention. So please be aware of that. Heat is not something to play around with. It can do really serious damage to your body. So from there, looking at, actually got two related ethical, I'm not sure what's going on here, that keeps popping up. Two related ethical dilemmas in science. The first one is taking a look at the energy consumption. And so during periods of peak energy usage, energy companies must balance supply and demand. And so they've got a limited amount of electricity that's going to be available. When that demand starts to exceed the supply, they can try to increase the supply. They can try to, obtain electricity from another provider, but chances are if it's hot here, it's going to be hot there. The other provider is probably strained as well. They could ask consumers to voluntarily conserve energy, so run appliances like dishwashers, washers, dryers at night when it's cooler. But in some cases, companies will go to rolling blackouts where they'll basically kind of reduce the power supply to portions of their grid, portions of their consumers for short periods of time to prevent kind of an overload of the system causing a very severe outage. So the questions are this: during these periods of peak usage, should power companies be able to reduce a consumer's energy consumption by reducing their air conditioning? And so this is a report of a Texas electrical provider taking a look at this, and it's not showing up real well on this slide. We've got the energy that's being produced, and then the blue line underneath it is energy consumption, and we can see during periods of peak usage that energy consumption line is coming up and getting to that energy supply line. Some energy companies have the ability to kind of regulate your air conditioning, so turn off that compressor for a period of time, but continue to run the fans. PECO had a problem. The electricity provider to Philadelphia had that program for about 10 years ago, but it was just discontinued in summer 2021. Should a program like this that controls energy usage be voluntary or mandatory during periods of high use? And then should there be incentives to increase participation in this program? When I lived in the Philadelphia area, I think it was a $25 reduction in our electric bill if we were a part of $25 per month if we were part of this program. The second ethical dilemma in science related to this: studies show that long-term exposure to air conditioning can weaken thermal adaptability, the ability to respond to those increased temperatures. So should air conditioners be regulated to prevent excessive cooling? I think we've all gone into locations where the air conditioning's on and you want to put on a sweater because it is frigid in those areas. And so is that too excessive? Is that kind of a waste of energy? Is this not kind of a responsible use of air conditioning? Should there be incentives to reduce the heavy reliance on air conditioners by healthy people? Such as using fans and dehumidifiers. It's not necessarily going to get it down to the very comfortable 72 or 74 degrees that many of us would enjoy, but it is kind of a more reasonable range if we're worried about overloading the system. So a little bit longer than I planned on this one, so maybe watch this on 1.5 speed. But as always, thank you for listening to this Ethical Dilemma in Science. Please see the descriptions below for additional information and references. Thank you, and have a great week.